This conference will now be recorded.
Good morning, everyone. Welcome to the day three, and I'm somebody's talking. And today we will. Myself is Bhanani Chandrakumar. I am an academic at GMR Institute of Technology. Today we will discuss about pole placement controller and an applications to and its application to a DC motor. So first of all, we will go through the recap what we have learned in the past 2 days. We started our discussion with control system. What is a control system and what are the applications of control systems and fundamentals and fundamental aspects of the control system. And then we have seen the open loop and closed loop system. And through simulations, we found out what is the requirement of the closed loop system. And in the first case, we have taken a very simple system, but we have intentionally we have taken that it is the integral action is embedded in the system, that is 1 by s into s plus 5, and then we have designed the proportional controller, and we saw that uh, only the proportional controller can able to deal with the steady state error. The reason there is because the plant itself has an integral action, integral action is there. And the next we have considered another plant where we have seen that if the plant doesn't have integral action on its own, then by using only the P controller, the proportional control, it is almost impossible to make the steady state error as zero. For that purpose, what we have used is we have gone for the PID controller. We have seen the theoretical aspects and what are the particular parameters, the effect of the particular parameter on the second order time domain response. For example, we have seen that the proportional controller improves the rise time, whereas the integral reduces the steady state error. And if we use the derivative control, it improves the overall stability. But the caution is that one should not use the derivative control unless it is required due to the practical implications. And then we did the open loop analysis of a DC motor, and we saw that it doesn't yield desired specification. And then we have gone for the PID controller tuning, auto tuning, and how to tune. This is very much important, and we have discussed how to do the PID tuning automatically in a minute. In 1 minute, you can design the PID tuning to get the various KP, KD. So this is one such method which will require only 1 minute. However, in the research literature, if you see, there are hundreds of methods. Somebody uses the genetic algorithm, somebody particle small optimization, somebody fuzzy logic, somebody backfly algorithm, firefly algorithm, bat algorithm, so on. So one has to use those algorithms unless if it is required. And we have seen that it is not required in most of the cases. And with using only one particular in 1 minute approach, we can able to find the KPK gain. It doesn't matter what method you are using. Either you are using Ziegler-Nichols method or you are using any other methods. Only the final thing what you required for the realistic implementation is the three gains KP, KI, and KD. And we have seen how to find those effectively by using the MATLAB autotuner. Uh, I don't represent here the MATLAB, so you don't think that I am from the MATLAB and I'm just selling the product, but I'm telling the fact what it is. So then we have seen the PID control of a DC motor, and I have given the assignment as well to one of the research paper to look into it. I don't know how many of you have looked into it, but before that, I would like to know how many of you got the PID controller, what we discussed yesterday, and what we have seen in the video. I only can see that only 90 of you have seen the video. So out of 120, 90 is around around 80% or so. Uh, could you please put it in the chat box how many of you have got how many of you got the results for the DC motor what we discussed in the class, not the assignment one. Could you please in the chat box? I would like to see how many of you have uh, how many of you could just write yes, yes, yes or no. That's it. Nothing more than that. How many of you could able to do the simulations of a DC motor PID controller what we discussed yesterday? good. Good amount of people have done. Saurabh, Praveen, Soumya, Subhashri, Murgesh, Sai Teja, Khadija Khatun, Janala Harshita, Sai Kumar, Shashi Kumar, Niharika, Monica, Samal, Uday Kumar. Yeah, okay. So good number of you have could able to do this one. So yeah, so that's good. I'll share the screen because I cannot see the chat if I am in the share mode. Yeah, now it is better. Okay, so this is the recap of the 2 days. Today we are going to discuss another important control strategy, which is called as the pole placement controller. So before going into the pole placement controller, I would like to give some emphasis on what is poles and how it is related to a system dynamics and so on. So let's start our discussion. So this pole placement is completely a state space model. That's why yesterday I had derived the state space model, but someone has told that there is no need to derive the state space model as in the feedback. But it is very much important for the other participants. That's why I have derived. So consider the state space model x dot equal to x plus bu and y equal to cx plus du. So this is called as a state space model. Those who have not studied the advanced control systems or in some of the curriculum, this advanced state space model is not included in the fundamental control system. So this x dot equal to x plus b, y equal to cx plus d. This how to get this one. We have seen two different examples. One from the RLC circuit also we can able to get the ABCD matrices, and yesterday's DC motor we have derived how to obtain this ABCD matrices. So where the x is called as a state vector and y is called as the output vector. The A is called as the state matrix, B is called as an input matrix, C is output matrix, and D is a transmission matrix. And this Y is called as an output, and this X dot is called as a state derivative. For a linear time invariant system, generally we are dealing just for the simplicity, we are dealing with the linear time invariant system, where this A, B, C, and D are constant matrices. If it is linear time varying system, if the system varies with respect to the time, then this A, B, C, and D will be the elements of these matrix could be the time varying function. Like instead of one, it could be t plus two or t square and so on. It is important to note that the state space representation is not unique. That means for a particular system, there can be hundreds of ways of representing that particular system in the state space method, state space models. However, when you convert all of them into the transfer function, then you should get the unique one. That means if you take a particular DC motor model, with the DC motor model, there might be hundreds of state space representations. Some of the standard representation are control canonical form, observable canonical form, Jordan form, diagonal form, and so on. So whatever be the form, if you convert your system, then finally, if you convert it back to the transfer function, it will you will get the same. You should get the same transfer function. That means state space approach is not unique, but the transfer function is unique one. So one can change the state space to transfer function and the vice versa. Manually also you can do it. There are different ways, or using the MATLAB command SS to TF and TF to SS. These are the two different commands by using you can SS to TF means state space to transfer function, and if you want to convert the transfer function to state space TF to SS, there are many other arguments as well required for this one. For example, if you want to convert the SS to TF, you need ABCD, which will give you the numerator and denominator. Then you can convert it to the transfer function. If the transfer function is there, the transfer function to state space, if the transfer function to state space is there, then ABCD should be your output arguments, and the input arguments are or the numerator and denominator, and the vice versa. This we will see how to do this even in the coming classes. So this is all about the state space. So some important points to remember about the state space is, in general, we consider the states which are time varying, which are varying with respect to the time. If you take the constant, if you consider some of the states as a constant which are not varying with respect to time, let us assume R, L. We assume that if it is not varying with respect to time, if you take the derivative of that particular constant, it will become zero and it is useless. You cannot do anything. So that's why the states, whatever you are considering, should should vary with respect to the time or so on in general. For example, the currents, voltages, speed, and those kind of elements one can consider as the states. And the output generally, if it is a full state feedback, if I'm saying it is a full state feedback, then all the three states what you are considering, then that can be considered as output as well. Otherwise, in general, some of the states only a partial state vector. So that is one thing. So next thing is what we will see here is and how to represent a particular state space model in the Simulink or in the block diagram approach. So this is x dot equal to ax plus bu, y equal to cx plus du. For this particular case, I assume that t is 0. Uh, this is very important. Carefully see what is happening. Whatever you are seeing, this integrator is 1 by s. In generally, it is represented by 1 by s in the Laplace transform. So what is happening here is this is x dot. This is the block diagram approach. This is x. X dot, if you integrate, you will be getting x. And this x is multiplied with this gain block a. So this is a into x. So here what you are getting here is a into x plus another thing, another signal which is coming here. This signal what is going to this particular summer is u b into u. So that's why you can see that x dot equal to ax plus u. Once again, I'm telling you x dot equal to x is coming from here a into x. This particular point is a into x, and this particular point is b into u. B is multiplied by the input signal which is going into this block b into u. So here you are getting x dot equal to ax plus a into x plus bu. So that's what this first expression. In the second expression, what I'm saying it y equal to cx plus d. If I assume this d as 0, x is coming from here, y equal to c multiplied by x. So y equal to cx. I assume that d is 0. However, if d is not 0, so this is the actually Simulink representation. So what you can see here is, I hope it is visible. So this is the input u. So b into u is going to this particular block, and this is the x. A into x is going to this block, and y equal to, if I assume that cx plus du, if I assume that y equal to cx plus du, c into x. So this is the x which is coming here, and d into u. So this is the u. So d into u. One thing you have to note here that when you select this block, you have to select k into u. It doesn't mean that if it is written here u, it doesn't mean that if it is written here u, it is the input control input u. It means that whatever the input signal it is going, that is the nomenclature for in the MATLAB for the block gain block. Whatever the signal is coming inside this particular block is represented as u. So here what is coming inside? This is the x. So x is going here. So that's why a into u means a into x here. So here actually that u use the control input. So b into u. Here c into u. U means here it is an x because x dot you are multiplying to get the x. So c into x plus here it is u, d into u. So this is the way one can represent the state space in the block diagram approach. So this is very much important for analyzing the state space model. And this I say it is an open loop state space model because the control whatever here you are getting here, it is just some random control it is going in. It is not dependent on any kind of the feedback mechanism. It is not coming from here. So u is independent of any states or something. Just you are giving some input and you are seeing what is happening. So this is called as an open loop control. So this whole thing what you are seeing here, it is called as a system. So this is this whole things, the system u and y. So this is a kind of open loop system. Okay. So some of the important concepts what one has to go, what one has to learn before designing the pole placement controller is controllability. All of you carefully read this thing, then I will explain you what do you mean by controllability. A system is said to be completely controllable. I'm excusing the caller 11 and caller 13. I don't know who they are. I'm just removing from the list. Caller 20, because they have not even told to me. Caller 11, 39, and somebody is there 39. Instead of 100 times, if they're not, following this thing, then I'm helpless. Yeah, fine. And I'm going to lock this meeting as well now. Yeah. So a system is said to be controllable if it is possible by mean of an unconstrained control vector to transfer the system from any initial state to any other state in a finite interval of time. So it looks a very big statement. Let me simplify for you. The first line, it says that a system is said to be controllable. So first of all, for any control system in general, the system should be controllable or it should be detectable. We will not go into the it should be stabilizable. We will not go into the stabilizability aspect. What we are going to see here is a system. When can you say system is controllable? If it is possible by means of an unconstrained control vector, that means you have infinite control input force. If you apply that infinite control input force which is available with you, if you apply to a system, and if you could able to transfer the system state from any initial state to any other state. For example, for the system state, let us assume for the DC motor, the system state is the speed. If the initially the speed is 0, and if it is possible by applying the control, if it is possible by applying the control input, if you can move the initial speed from 0 to any desired speed, let us assume for 1500 or 2000, whatever it may be. Theoretically, if you have infinite number of infinite control is there, then you can move the corresponding state from initial value 0 to any RPM. So that's what I mean to say here is, and you can only design the control systems, the feedback controller, or the pole placement controller, if the system is completely controllable. That means if the system is completely controllable, then only you can design the controls pole placement controller. One such example or one such physical realization, what I will say, that when can the system be the controllable? For example, in very simple case, you can, if the control doesn't have any effect on the states, if the control doesn't have any effect on the states, then you cannot control the system. For example, if I'm sitting here, if I'm sitting here, and if I want to control the participants who are attending this lecture, I can control through the various GoToMeeting app controls. Suppose if I want to remove someone or if you want to add someone, that all controls I have. But I may be, the whole system will be uncontrollable if you have not logged into the GoTo app or if you don't have the internet facility. So you can see that though I want to control you, the intention is good for the other participants, for the sake of other participants. But since you have not logged into the system itself, I cannot control. That means I don't have access to you. So that is called an uncontrollable system. So many such cases, if the system is uncontrollable, you cannot control the system and you have to live like that. So mathematically, this is the philosophical definition. Mathematically, A, B matrices and so on, this N is the order of the system. For our DC motor, the order of the system is 2. It is a second order system. So the rank of the below controllability matrix should be equal to the order of the plant. The rank you can find out, by various methods. The simplest thing here, we are only interested in if the controllability matrix is full rank or not. You just find the determinant and determinant. If determinant is not equal to 0, and hence you can say that it is full rank. Otherwise, there are many other methods. Echelon form converted to various forms, and you can see what is happening. But the simplest thing is, because we are not interested in finding exactly the rank of the system, we are interested only if the system has full rank or not. If it is a second order system, if the rank is 1, it doesn't matter to you. It should only be matter. You should only focus on whether the system has full rank or not. If the system has full rank, that means if the rank of the system is equal to the order of the plant, the determinant is not equal to 0, then you can say that yes, the system is completely controllable. So that is the one what you can see. So so this is called as a controllability of a particular system, how to find mathematically. And I will tell you how to do it using the MATLAB as well. The next thing is the poles of a system. So these are very important things because we are completely as one. If we say it is a pole placement, so there the main component is the poles, and we should know what are the poles of a system and how it implicates how the system response can be determined from the poles or so on. So poles. So as far as the transfer function is concerned, you might be aware there is a numerator as well as a denominator. If you equate the numerator to its 0, then whatever the corresponding x values we are getting, we call it as the zeros. And similarly, if you equate the denominator of a transfer function to 0, then we call it as the poles. Why the names zeros and poles are coming into the picture? For example, if you substitute the same value, if whatever any one pole value in the transfer function, assuming that it is in zero pole gain format, then the system will become infinity. That means it is very far away. So that's why pole, south pole and north pole are very far away. That's why if you substitute the pole values, whatever you're getting in the denominator of the transfer function, then the 1 by 0, whatever be the numerator, the denominator will become 0. And hence the whole transfer function will become infinity. That means system will look, uh, the, the system is at infinity means the poles which are very far away, south pole or the north pole, which is very far away, that's what we call it poles. And the second one is zeros. Why the name zeros has come? Suppose if you equate the numerator to 0 and any of the value which we are calling it as zeros, if you substitute back in the transfer function, then your transfer function will become 0. So that's why it is called as a zeros. So the order of the system is equal to the number of the poles. So if it is a if it is a second order system, it Shadab, please be on mute. Saeed Shadab 1107. Thank you. Yeah. So, again, I had to recall what I was discussing. Okay. The order of the system is equal to the number of the poles. So,
Sir,
what we have
please check
seen here
your
is,
network. It is disturbing, sir.
hello,
There is a network issue.
hello.
Sir, please check your network, sir. It is a quite disturbance, sir. The video is tracking.
No, it is fine from my side. I'm using the high bandwidth. I think it could be problem for your side. I'm using the
Okay,
high
okay, sir.
bandwidth. Yeah, it is a
I think,
LAN cable.
yes, sir. From the beginning, it is like that, sir. So that's why I'm saying.
No, no, I think it is a problem from your side because nobody else has, uh, can anyone can please tell us whether is there any problem from your side? Can you able to see my screen?
No, sir, it's rude.
Sorry.
The screen is okay from here.
Hello, Kasim. Could you please respond?
The screen is okay and very
Can
clear.
you?
I can
The
see you
screen
and,
is clear.
and the screen is very. Hello?
You can see the screen. Can you able to see the screen, Kasim?
Yes, I can see the screen is clear.
Yeah, I think the problem here is since the people sitting at Nigeria can see. I think it is not the problem from my side. Can anyone else respond from? Let me.
Sir, good morning, sir.
Yeah. Good morning.
Screen is visible, sir, but audio, no, it is some few disturbance at some times, sir.
Yeah, the
The
disturbance is
audio is
coming
coming.
because because
The
somebody has
audio.
logged in. If
Okay, okay,
somebody
sir.
is if somebody is logging in, the disturbance is coming. That's why somebody has logged in. I told the particular person name as well who is logged in. So that was the
Sir,
reason why the disturbance is coming only from the participant. If somebody is talking, if they are not in the mute, then the disturbance is appearing. So that's why I'm requesting everyone to to be on mute mode.
Yes, sir.
Okay,
Now
sir.
it is.
Okay, sir.
Yeah. Okay. Okay. So let me again explain these poles very quickly. So the poles can be determined by equating the denominator of a transfer function to 0, and the order of the system is equal to the number of poles. So yesterday we have seen the transfer function of a DC motor, which is s square into something. So that means there are two order. The order of the system is 2, and hence the poles will be the 2. And generally, how do you find the poles of a system? From the system matrix A. What you can say that the system matrix A, the eigenvalues. So since it is a 2 by 2 matrix, there will be two eigenvalues, so which is equal to the order of the system, and hence if you convert it back to the transfer function, so it will be the second order transfer function, and the vice versa. And these poles, one can analyze the stability of the system from the poles as well. So this is very much important. If I, if you know the poles locations, you can tell about the stability. A very simple answer is, how do you do this one? For this, a simple answer is, if all the poles are on the left half of S plane, then the system will be stable. So that means you have to ensure that if you want really the stable response, then you can place all the poles on the left half of S plane. Okay. And the next thing is closed loop poles locations and desired specifications are closely related. So suppose if your open loop system has some poles on the right half of S plane, by using a suitable pole placement controller, what you are going to do here is, whatever the poles on the right half of S plane, you are trying to bring it to the left half of S plane. So that is one particular case. That means to stabilize the system. Stabilizing means the poles which are on the right half of S plane, you are trying to bring it to the left half of S plane, and the system is stable. That is one case. The another case is, even if the system is stable, but if it is a slow system, then by placing the poles at an appropriate location, you can make the system fast. Then how the slow and fast, that completely depends upon the pole location. A simple thumb rule is, if the poles are near to the origin, then they are a bit slow in the nature. So those particular poles, generally those particular poles will create the sluggishness in the system. That means those particular poles are responsible for the slow response of your system. So what you have to do, if you want a faster response, those particular poles, you need to move it bit farther from the imaginary axis. The poles can be imaginary or it can be the real as well. So if you want the faster response, you have to place the poles farther from the imaginary axis. But if you keep very far away the poles from the imaginary axis, then the system will be very, very fast. That means, in other way, if the poles, if you're keeping at minus infinity, then your system response is within 0 seconds, you can able to get the desired, settling time and so on. But that is theoretically. But practically, if you keep the poles very far away, those system will be very fast. But if you see from the frequency domain point of view, the bandwidth will be very large. If the bandwidth is very large, noise is a high frequency phenomena, and the noise will enter into your system response. So that's why, as a control engineer, when you design any controller, not only you have to focus on the time domain, at the same time you have to satisfy the frequency domain specifications as well. In this SDP, we are not going to go much in details into the frequency domain, but just for the sake of practical concern, I'm going to tell you what is the frequency response and so on. In general, you might have heard about the gain margins and phase margins. So desired, we have seen that if it is desired time domain specifications, we have seen rise time, which will tell how fast your system is. The peak overshoot, the maximum, the value which you can allow your system to go. The peak time, the corresponding time at the peak overshoot is called as a peak time. And settling time, when your system settles within the tolerance band of 2 or 5%, it is called as a settling time. And the steady state error. Steady state error means if your system reaches the steady state after all the transients are died out, and if your system reaches exactly to the reference input, then we call it as steady state error is 0. That means if you are giving the reference input as 1, and after a long time, as t tends to infinity in some cases, if that particular value or the particular output goes to 1, then you can say that the steady state error is 0. Otherwise, Otherwise, you can say that the steady state error is non-zero. So the closed loop pole locations and desired specification goes related. That's what I told. If you want the fast settling time and faster damping and the other things, you should place the poles farther from the imaginary axis. Otherwise, you can, if the poles are near to the origin, there is one more practical issues. If you are placing the closed loop poles very close to the imaginary axis, let us assume this is the imaginary axis, and if a pole is very near to this imaginary axis, due to if there is some small disturbance in your pole location due to any physical considerations or due to external disturbances, then there is a chance that this pole will move to the right half of a plane. However, if the pole is very far away, even if there is small disturbance or some parametric variations due to which your pole will move little bit here, but it's not going to the right half of its plane. So that's why. So if the pole is very close to the imaginary axis, then there is always threat that it will go to the unstable region or the right half of its plane. Or if the pole, in other ways, if the pole is very close to the imaginary axis, then it will give you the sluggish response, slow response as well. So the poles need to be placed appropriately, mostly in the left half of S plane. If you want your system to act as a then stable response, then the poles need to be placed in the left of S plane. In 99.9% of the cases, you want your system to be stable, behavior to be stable. In 0.01% cases, you want your system to inherently, you will design a controller so that the system will become unstable. There are some cases. So 99.99 cases, you will only go for the systems which you will only design the system for the stable response. That means poles need to be placed appropriately, mostly in the left half of S plane.
Sir, sir,
Yeah.
doubt, sir.
Yes. Yeah.
Sir, usually when we define a transfer function, we have poles in such a manner that is k by s minus 1 into s minus
Yeah.
12. So we have poles as 1 and 12 on the left
Yes.
hand side. So we can say
No, as
that this
1 and
pole,
12 are on the right hand side. Ms. Serena, 1 and 12 are on the
sorry,
right
s
hand
plus
side.
1, sorry, s plus 1 and
Yeah,
s
if you're
plus
saying it,
12.
yeah, but then that is fine. The poles
Yes.
are on the left half of S plane. Yeah.
We say that this 12 pole 12 is insignificant pole and 1 is significant pole. Why we say
Yes,
like that?
yes. Because the 12 which is very far away from the system imaginary axis, so the time response for that pole, the 12 is very fast. That means it will not affect your system. The pole which is affecting the complete, which is dominating your system, is which is at 1, because 1, that means very near to the imaginary axis, and hence it will slow down your system. So that's why we call that pole which is very near to the origin 1 as the dominant pole. And as I told, there is always a threat that if there is some variation in the plant parameters, that one dominant pole, one can go on the right half of a plane as well. So this is due to the two factors. One is it completely detects the system, sluggishness of the system. And the second one is there is always possibility that the plus one, which is near to the imaginary axis, by due to some considerations, some plant disturbance or some parametric variation, there is a chance that it may go to the unstable. So if you can see that if you give a little bit push to the pole which is at -1, if you are pushing that through to by using some kind of force or some kind of uncertainty, by using 1 unit, you can only 1 unit is required to push that to the right half of S plane. However, the pole, that's why we call this dominant pole. It is completely dominating the system response. But the pole which is at -12, if you push by 1, so it will going from -12 to -11, but still the system is completely stable. So it is not completely, so the pole which completely dominates the system response, which is near to the imaginary axis, that is called as a dominant pole. And we should be worried only about the dominant poles itself. We should not worry much about the poles which are very far away from the system response. So that is my answer. Is it clear?
Yes, sir. Yes, sir. So after
Yeah.
that, when we find the DC gain and all, we only retain the dominant pole. We just remove the significant pole. So what's
Yeah.
the relevance of that?
Yeah, because there is no need to control that that pole which is very far away from it. Is already it is giving you the good stable response, good response, faster response. So you don't need to control the pole which is very far away from the origin. So only the thing is, only the pole which is near to the origin, you have to focus on that one itself. So that's why you are,
Okay,
for
sir.
most of the cases in the design, you are removing the pole which is very far away from the system, from the imaginary axis.
So
Yeah.
we need to control only the dominant pole.
Yeah,
That's
you
what
need to
you are
control
saying.
mainly the dominant pole itself. Yeah. And that
Okay,
depends
sir.
upon,
Thank you
suppose
so
you
much.
want the pole to be minus 1000, but your pole is
Mhm.
at minus 12 and minus 1. Suppose if you want the pole to be placed at minus 1000 and minus 2000, then you have to control both the poles.
Okay, sir. Thank you. Thank you so
Yeah.
much.
Okay. 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 So now we will go to the next. I hope this poles of a system, this concept is clear to all of you. So now I will go to the next part. So this is again the state space representation of the open loop plant x dot equal to ax plus bu. Again, this x dot a into x plus b into u, y equal to ca. So this is the open loop plant. However, this u is the one which we need to control. And as far as state space pole placement controller is given, this u equal to minus k into x is the one. U equal to minus k into x, where k is the pole placement controller gain which we need to find out. This pole placement gain is similar to, kp, ki, kd, the gains. It is just the numbers. So how to find these numbers, that we will see. So this is this block diagram, this complete block diagram. What you are seeing here is the closed loop pole placement control. When I'm designing the pole placement controller, I'm only worried about the A matrix and the B matrix. C matrix doesn't come into the picture directly. Okay. For the design, I only need A and B matrices. So consider the plant x dot equal to ax plus bu, and I'm saying the state feedback control u equal to minus kx plus r. If this r is 0, if the reference input is 0 in some cases, then u equal to minus kx. So my closed loop plant, so what I'm going to do here is, whatever the structure I have assumed state feedback control or the pole placement control, if I am substituting here u in the u, that is x dot equal to x plus bu, if I substitute this u in this particular closed open loop plant, then that will become as the closed loop plant. So x dot equal to, Hemasri, could you please be on mute unless you have some query to ask? So half of my time is going in, asking the people to be on mute. Please understand. So ax plus b into u. So this u, if I'm substituting whatever this control structure here, then if I'm rearranging, what I'm getting is a minus bk into x plus b into r. So as I'm saying that, now this a, instead of a, my system has become closed loop system has become a minus bk.
Sir, I think you are not audible.
Sir, you are not audible, sir.
Sir, you are not audible.
Yes, sir. Yeah, hello.
Sir, now it's okay, sir.
Okay. So x dot equal to ax plus bu, ax plus b into this one. So now if I rearrange, I'll be getting a minus bk into x plus b into r. So the same thing, if I'm going to represent here, you can see that this complete thing I'm going to represent x dot, this is the x dot equal to a into x So b into u, which is coming from here. But as we see that u is nothing but minus u is minus kx plus r. So this is coming the x here. So this is minus kx, since this minus is absorbed here, minus k into x plus r. So u is minus k into x plus r. So this summation block, okay, and x dot equal to x plus bu, then y equal to c is the same thing. So this is the whole structure of the pole placement controller. So what is unknown here is this k is unknown, and this is called as a pole placement controller gain. So this k is unknown here. So this is called as a pole placement controller gain. Okay. So how to find this gain is the complete, that is the main thing what you want to do for the pole placement. Once again, I will repeat: x dot equal to x plus bu, u equal to minus kx plus r. So why we are calling it state feedback control? Because the state, all the states are getting fed back to the for the controller design. However, in the PID controller, it is an output feedback. The output is fed back. But here all the states. So all the states should be measurable. That means if the system has two states like the current and speed for the DC motor, you should have the two sensors: the ammeter for the current and the tacho for the speed. Uh, so so this is u equal to minus kx plus r. If you substitute this structure here, and if you rearrange, you will be getting a minus bkx plus br. So the closed loop poles, the desired pole locations, wherever you want to place. So by choosing an appropriate value of k, you could able to place the desired poles. That means the eigenvalues of this a minus bk, the eigenvalues of a minus bk should be equal to the desired poles. So that's what I mean to say. And so again, so that's what I'm saying is we can control the closed loop pole location by finding appropriate values of k. In this case, this allows us to select the position of all the closed loop system roots during our design. So this will ensure that my closed loop poles are at the desired location. How do you find the desired location is a big question that we will see. Okay, so this particular, whatever the in its naive form, pole placement control, whatever we have discussed here, it will ensure that overshoot, settling time, everything will be in the reach, but it will not ensure that the steady state error to zero. It will not, we cannot force the steady state error to zero if we use this pole placement controller in its naive form. However, there is what we have learned from the earlier classes is that if you use the integral action, then there is always a possibility that you can able to eliminate the steady state error completely. So the pole placement controller, when you want to eliminate the steady state error completely, so we have to use the integral action. So this integral action will try to eliminate the steady state error, the error which is coming, uh, the output minus reference, this error will go to the zero. So how that is happening, this is the integral, and whatever this state we are saying it is xn. So here it is xn dot, which is nothing but error. If you integrate, uh, you will be getting the xn. So this particular thing, xn dot equal to r minus c into x. So c is here, c into x. So this error is nothing but r minus c. This particular point is, it is coming from c into x. This is why c into x. So this is xn dot. If I'm integrating, you are getting xn. Then some gain ke is required, which is now been added to the u. Earlier u was only minus kx plus r. But instead of this one, now what you'll be getting here is, instead of only this minus k into x, you'll be getting another term which is ke into xn. So if you use this particular structure, it will ensure that the steady state error will also go to zero. We will see how we will use the simulations to see practically what is happening. So now what I'm going to do here is, there are two systems. First of all, I had to form the augmented system. So this is my actual system. So this is another state I am adding to the actual system. So if the state here, if it is second order, then if I adding one more, then it will become the third order system. This is called as augmented state. So the first thing, if you see x dot equal to a into x plus b into u plus R term is not there. So that's why it is like this. X dot equal to, if I multiply like this, A into X plus 0 plus B into U plus 0. So that's why X dot equal to X plus B, the first element here. The second element or the second vector X n dot, if you see X n dot equal to R minus C into X. So that's why minus C has come here, minus C into X plus 0 into Xn is 0. There is no control U term 0 into U. And this R term is there. So Xn dot equal to R. So Xn dot equal to 1 into R. So this is my revised system or the augmented system. And similarly, y equal to c into 0 into xn. So what is happening? Y equal to c into x, right? C into x plus 0 into xn. So this is my revised state or the augmented state. And u, we have seen u equal to minus kx plus ke into xn. So that's what you have seen. U equal to minus k into x plus k into xn. Okay. So this is xn. So this is my new control input for the augmented system. And this augmented system or the augmented pole placement controller with integral action has the capability to drive the steady state array to 0. And we will demonstrate this with by using the same our DC motor example. So the basic steps to involve for the pole placement controller, this is a procedure for the development. This is the basic steps involved in this. First of all, you have to check the controllability of the system. If the system is completely controllable, then only you can place all the poles at the desired location. You can use the CTRB is the MATLAB command. We will see how to do this one. If the plant is completely controllable, then the pole placement can be designed. And the next thing is you have to select the desired closed loop poles. And this desired closed loop poles can be selected based upon the plant at hand. If you want your system to be very fast, then place the poles very far away from the origin. That means, for example, the system which are very fast are power electronic devices, where you want the settling time to happen in microseconds or even nanoseconds as well for some applications. So for those kind of particular systems, you have to place the poles very, very far away, like minus 100,000 or so on. If you think that your system cannot able to, due to its inherent capability, you cannot able to, so that much faster response is not required, you can place the poles at minus 10 or so on. For example, the nuclear reactor, which is a bit slower thing, where the settling time in few hours, then accordingly you have to place the poles, and you have to ensure that again, if you're placing the poles very close to the origin, you have to ensure the stability as well. So that whatever be the case, whatever the external disturbances or parametric variations happens in the plant, it should not move your desired poles from the particular whatever the location you have selected to the right half of its. For the stability, all the poles should have negative real part. That's what I say. If at least one pole is on the right half of S plane, then system will become unstable. And once the desired poles are selected, then the pole placement gain K, the K can be calculated using the MATLAB command place or occur. And then the pole placement control can now be written in a U equal to minus Kx. This is very naive control, very naive form. But in some cases, if R is there, plus R will come. In some cases, if you are using integral action, then plus Ke into R will come into the picture. So this is this U equal to minus K. This is a very simple form when R equal to 0. That means there is no reference input. You want your states to go to 0. So again, this is the DC motor model what we have derived
Excuse me,
yesterday, and you
sir.
might.
Excuse me,
Yes, hello.
sir. Sir, the system will have two poles. Let us say, sir, if we
Yeah,
put,
please tell.
if we keep one more pole in that, then it doesn't change the character of the entire system.
That I didn't get, sir. The complete
Suppose a system
idea of the.
have two poles, sir.
Yeah,
System
let
will
me
have two.
explain, sir. Let me explain, sir.
Okay, sir.
If the system has told two poles, then your closed loop system should also have the two poles. That is the complete philosophy of the pole placement controller. So you cannot
Okay,
select the number of poles. That's what I said here. The desired pole should be n poles itself. So where n is your actual system order, you cannot select the poles which is very far away from the system. So not far away, which is another pole. Suppose if the system has two poles, then the closed loop poles also should be the two. There is no point in third pole and making the system complex. Okay, sir. So the desired specifications here, what I'm going to select is settling time is less than 0.06 seconds. That means I want very, very faster response. Overshoot should be less than 5% and zero steady state error. This DC motor model, what we had discussed, I have taken from this University of Michigan University, this web page. Okay, this is the one. So let's see what is going to happen now. This is the code I have written. So the one code here we are going to see the response from two different aspects. One aspect is we are going to see from by using the coding, and the second one by using the transfer function, by using the Simulink approach or the block diagram approach. Both of the things will give the same response. So first of all, I will explain this thing. I will zoom this particular thing. I think now it should be visible. Okay, so clear all, it will clear all the variables from the workspace. CLC, it will clear the screen. Close all, it will close all the figures. These are the parameters of the DC motor which we need. And these are the state space matrices A, B, C, and D. So what we have obtained. So this is the way to represent minus B by J, K by J, and so on. And state space model DC underscore motor underscore SS. So what I'm saying is state space model. If I want to combine ABCD in a particular variable, which I'm calling it as DC motor SS, so which is nothing but state space. This is SS means state space of A, comma B, comma C, comma D. This name you can give anything in the left hand side, but this SS is the inbuilt command which you should give the SS itself. You cannot change this one. And I told next I'll be doing the controllability test. So for doing the controllability test, first of all, you should know what is the order of the system. You can find out the order of the system. If we know from this particular thing, it is order of the system is 2. But if the order of the system, if it is not known, if it is 10,000, if you don't want to calculate and so on. So the simple command order of DC motor SS, so state space DC motor model, if you see, it will give you the order. So it is 2 for our particular equation. And the system rank, what we are saying, that rank of the controllability matrix, CTRP of A, comma B, it will give you the controllability matrix. And the rank of the controllability matrix, this rank command will give the rank. So system rank. So this order will give you the rank, the order of the system, and this rank will give you the rank of the controllability matrix. If, as per our definition, if the system order equal to the rank of the controllability matrix, it will display the plant is controllable. Otherwise, the plant is uncontrollable.
Sir, a doubt, sir.
Could you please ask? We will have the doubt session once I complete this discussion on this one.
Okay.
Yeah, because it might be interrupting others as well. So we can have the discussion once I complete this, because it will deviate the participants. Okay, so now what is happening here is, yeah, so this will tell us whether plant is controllable or uncontrollable. If it is uncontrollable, leave it. You cannot design the pole placement controller. Then the desired poles, I have selected as -1000 and -2000 because I want very faster response. And the pole placement gain, the K, which will K with the command place or ACK or occur, will also give you the same thing. A, comma B, comma P1, P2. So these are the desired poles. So for designing the pole placement controller, you need the A matrix, you need the B matrix, and you need the P1 and P2. And to plot this one, T equal to, so what I'm interested only till 0.05 seconds itself. Because why I am interested only in 0.05 seconds? Because I want all the system to settle within 0.05 seconds or 0.06 seconds. That's why I am taking the time only till 0.05 seconds itself. Then the system closed loop system, what we have seen earlier, A minus B into K. So my A has become, so my closed loop system A minus B into K has become, then B, C, and D, the same thing. So I'm forming the state space system, the closed loop system now. In the earlier one, this minus BK was not there. So this minus BK PPC or the pole placement controller has come from the discussion what we discussed. And the step command will plot this closed loop system step response. And this grid means you will be having this grid lines. And this title, the title of this particular plot, whatever I'm getting, I'm calling it as step response with state feedback controller. So that is one thing. So I will explain the second code as well. And this is without integral action. When integral action comes into the picture, we have seen that this AA, BA, CA and DA are my augmented system. We have seen the integral action augmented system. So A into zeros, zeros of 2 comma 1. Zeros of 2 comma 1 means two elements, it will be 2 by 1 matrix of zeros. So 0, 0. So there will be two zeros. One is 0 and the another is 0. Why I am making it as 2, 0? Because for the this A is 2 by 2 matrix to just to ensure that the dimensionality, there will not be any dimensionality issues. We are considering zeros of 2 comma 1. And see, there is only one output. That's why only one zero is here. You are not considering the vector of zeros minus C. And the BA is B0 and the BR 0, 0 and 1. And CA is C0 and DA equal to 0. If you go back to the slides what we have discussed, so this will be the same thing. And the pole, so there will be third state as well. The third state is minus 3000 we are placing. So it is a third integral. So this three poles.
Sir, you may not be audible, sir.
Okay. So now this P3, whatever this P3 you are saying, this is the pole. You are placing the third pole, integral pole, because we have made the integral state. One more state has been added to the system. So to place that integral pole, I am saying that it is at minus 3000. So now what is happening here is Ka equal to place of AA, BA, and the three poles which is coming into the picture. So now T, again I am running for the 0.0505 seconds, and this is my closed loop system, and I am plotting the closed loop system response itself. So so what I have to do, whatever this code is given to you, the two codes you have to combine and you have to keep in only one particular uh, file, parameter file, and you have to run that one. If you run, you will be getting two different plots. What you'll be getting, I will be showing you. You'll be getting the two plots like this. And the one is the step response with the state feedback controller, and the another one is step response with the integral. So the important things to observe here is when I'm using the state feedback pole placement controller without the integral action, you can see that settling time is very good. The rise time is very good, very fast. Overshoot, this E means 10 to the power of minus. So when I say that E to the power of minus 14 means 4.44 into 10 to the power of minus 14. This 1E minus 6 means 1 into 10 to the power of minus 6. So, but here you can see that the final value is 1 into 10 to the power of minus 6, which is very small, which I can say that it is approximately 0. 1 into 10 to the power of minus 6. So my steady state error is 100%. That is that you can see from here as well. So this range is 1.2 into 10 to the power of minus 6, very small. I want the system to go at 1, but remaining all other things are satisfied. Only my steady state error is not going to 0, which is very, very important for my desired that is one of my desired specification. But here the steady state error I have 100% because I want to go into 1, but it is going into 0.0000112. So we very small one, which you can neglect, which you can say it is a 0. So the steady state error is 0. So this is without integral action. Now, if the second one with the integral action, if you see with the integral action, you can see that settling time is 0.005, very good. Rise time is 0.003, very good. And the final value, you can see that the final value is 1. That means my steady state error is 0. And the overshoot is 10 to the power minus 14, which is approximately to 0. So the overshoot is also 0. So this particular response with PPC with integral action, you can see that all the desired specification can be obtained. So the black one, which is, so I generally use the color coding. The black box is without the integral. So all the black things what you're seeing is without the integral. All these three are fine. Rise time, peak overshoot, settling time, it is fine. But only the steady state error, what you are seeing here is 100. So I want the steady state error to 0. So if I am using pole placement with integral, the steady state error has become 0. The remaining all are in the desired specification, all satisfies the desired specification. If I want to use this is the coding approach. The Simulink approach, this is the same Simulink what I have built. If you run that particular code, you will be getting kppc from the workspace, it will be saved. So this will so this A matrix, B matrix, C matrix, and kppc is already given to you. So this is, we have seen the block diagram. The same thing, you just copy as just develop this simple block diagram. Remind you when you are using, this is very important, when you double click this gain block, there will be 4 options. You have to select K star U, then only you could able to run this one, otherwise you cannot. So the same thing you can see if I'm running this one, the scope, you can see that this is 10 to the power of -7 into 10. So this is 1 into 10 to the power -6. So again, so that means it is very low value. It is approximately equal to 0. Since it has zoomed version, you are seeing something like that. Otherwise, it is flat at 0. You will, if the scale is 0 to 1, it will look as a flat at 0. So this is pole placement without integral control. And now I will show you with integral control. With integral control, what you need the 3 different gains. So one gain for the pole placement controller, the normal, and the third gain is required for the integral to suppress the steady state error to 0. That's what it is happening. So the same block diagram what we have seen, the KE what you have seen, so this is minus KA, the third element of the particular pole placement control, because the third element, the third pole what we are placing is for the integral of the error. So that's why this KA of 3 is coming to the picture. KA punished to 2. The first 2 poles will reflect for this closed loop system, whereas the third pole for driving the error, steady state error to 0. And you can see now the response, you can see that it has gone to 1 in 0.005 seconds or so, which is the same thing what you have seen here. So the 2 approaches will give you exactly the same response. So that's what I want to say. So next thing is, okay, I will not go into this aspect. So I am going to wind up this session now. So what you have to do here is you have to do the hands-on things. I will show you briefly how to do this one as well. I think I placed somewhere. Yeah. No, this is for the 2. Just I'm stopping this screen for a second, and then I'll get back to you. Okay, now the code is also ready. I will share my screen now. Yeah, you can see the same code what I have shown here. I have written here in the same file and have saved with parameters underscore DC motor underscore PPC pole placement controller. It is all the same ABCD matrices, controllability, and this is the desired pole locations. This is exactly the same thing, and this is for the pole placement controller with integral action. In the same plot, in the same code, M file, I'm writing both the codes. If I run this one, you can see the same thing. It is exactly the same. And this is for the pole placement controller with integral action. In the same plot, in the same code, M file, I'm writing both the codes. If I run this one, you can see the same thing. It is exactly the same. And this is for the pole placement controller with integral action. In the same plot, in the same code, M file, I'm writing both the codes. If I run this one, because I have taken this time interval as very small between two particular instance 0.001. It will give you the very smoother plot, but again, it has to plot for lots of values. So that's why it will take bit time based upon, it may not take more than a minute or so, or less than, since I have just started the MATLAB, it will take some time. So let it come and then I will explain you how to see all the time domain characteristics automatically, which has not been discussed in the previous classes. Now the code is running. So you can see that it is busy here. That means the code is running. Now, initially, once if you start the MATLAB and based upon your RAM configuration, the system might slow up. If you're running this parallel labs, then that will make the things worse. Yeah, these are the two things what you can see. At the first instant, both of them looks the one and or the same. But the important thing to note here is the system is going to 1 into 10 to the power of minus 6 or so. So how to get the characteristics? Right click, and there were 4 things you can see. The peak response. If you click the peak response, if you hover your mouse and if you click it here, it will show you the yellow things. Yeah, you can see now the peak overshoot is almost 0, 1 into 10 to the power of minus 6. And if I want to see the steady state error, you just use the steady state error. So this is the steady state error. You can see that instead of 1, it is settling it 10 to the power of minus 6. If you want to see another thing, settling time, you can see that settling time is 0.00471. And if you want to see the rise time, the rise time is fine. And similarly, this is for integral. So automatically the two plots will be there. Integral, I will show you the settling time. It's pretty much fine, 0.005. And the important thing here is you can see the steady state. Yeah, you can see that the steady state error final value is 1. This is the way to do this one. So I will give you this code, sample code and other things, and you have to develop on your own. The video I will give you. And this is the pole placement controller. So what I told to select here is, if you double click this gain block, so you can see that there will be 4 options here, 1, 2, 3, 4. You have to select the second option, this matrix K into U. And this gain block, from where you will be getting, you will get it from math operations. This math operations. So this is the gain block what you have to select, this gain block, and double click, and you have to write A, B, C, D, whatever you want. And if I'm running this one, if I run this one, this is the first time I'm running this MATLAB today, this Simulink file. That's why it will take some time. You can see this, the same thing what we have seen. The important thing to note here is 10 into 10 to the power 7. That means 10 to the power of minus 6. So this is 1 into 10 to the power of minus 6. This is without integral action. So only Kp, this is U equal to minus Kx is going into the one. And the second one is with integral action. You can see that the thing whatever I have shown here. If I run this one, it now ran very quickly. And you can see that now from the 0 it has started and it has reached 1. So the steady state error is 0. So the same things we have seen through the coding as well as through the Simulink as well. Now what I will do is I will share you the video link and the sample, the videos, the PowerPoint slides which is required for this particular, to run this particular code will also be given to you. Now you do it, and now it is 11:17 or 11:20, let's say. We'll meet at 11:50. Half an hour time I will be giving. The video is only for 15 minutes. If you exactly follow, It will not take more than even 15 minutes. So I'll be sharing you those things in a minute.
Sir,
So please, yeah,
sir,
hello.
what is KA 1:2, sir?
The two elements, we have the three gains, right? Two gains are for the plant and one gain is for the integral. So Ka is to 1:2 means first two elements of the Ka, which will control this plant, and the third element of Ka, which is the gain, pole placement gain for the with the integrator. So this third element of that particular gain will control the error, steady state error. There are okay, lot many things which we will discuss later. Somebody has asked controllability and reachability. I will discuss these points later. So in a way, reachability will implies the controllability in some way. So one and other are the same in several aspects. So I'll be sharing you this in a minute.
Sir, one more question, sir.
Yeah.
Sir, how to design the pole location, sir? You told -1000, -2000,
That's
-3000.
what I told. I have the deliberate details on that one. That depends upon the how fast your system response you want. I have selected my system response is 0.006 second, the settling time. That means very fast. That's why I'm placing the pole at very far away. If I say that my settling time of 10 seconds is also okay, and accordingly I will choose the pole very close, like -10 or so on, or -5. That depends upon the problem at hand. That depends upon the desired specifications and so on. So the pole locations you have to select, and this pole location is not the unique for all the plants. You have to select the pole locations based upon the problem at hand, based upon the desired locations at hand. If you simply change this pole locations, whatever I have given to you today, to different values, then it will slow down your response.
Okay, sir. For the faster response, let it be very far away. Any problem
Yeah.
is with that?
No, that's what you cannot keep very, very far away. If you are keeping very, very far away, then the settling time will be very, very slow. And the
Okay, sir.
frequency response, you will be giving more bandwidth, and hence the noise will come into the picture.
Okay, sir. Okay.
Yeah.
Sir,
So,
can I ask a question?
yes, please. Yes.
Sir, you told that when order is equal to rank, the plant is controllable.
Sorry.
Sir, is there any?
Your voice is not audible. Yeah. Could you please repeat
Uh,
again?
Am I audible?
Yeah. Now you are audible. Yeah.
Sir, you say that when order is equal to rank of a matrix, the plant is controllable.
Yeah, that is a
Sir,
standard
is that
discussed developed by Kalman filter, and there is a big theoretical explanation for that one. Yeah. Please tell. Yeah.
sir,
What is your question?
can we give any practical analogy for that or something? Can we relate that to so that the concept is clear
Yeah,
about the
the practical.
controllability?
Yes, the plant, if the states are directly affecting, if your voltage is directly affecting the states, then the plant is controllable. That means the voltage, it is coming from B into U, right? So voltage part from B matrix, it is coming into the picture, and your A matrix is the plant. So there is some relationship between the plant and the control. So U, it is affecting your the first state, and hence you can control the first state and indirectly the second state as well. However, if the U term, let us assume if it is a third order system and the last element, all elements are zero. Okay, the A matrix, all elements are zero, and your B elements are also zero. That means what is happening now, that voltage doesn't have direct implication on the state. So that means whatever the voltage, and hence if you find the controllability matrix, it will not satisfy the rank condition. It will not be full rank. And hence what is happening is whatever with the input voltage you are applying, it is not going to the, it is not directly, it doesn't have any effect on the particular what I can say that the input current, sorry, the current or the speed. That means in very simple way, 1 by L term is there in the B matrix. If L equal to 0, due to some reason, if that L has become open circuit or L equal to 0 due to the whatever the reason, due to the failure, your control will not have effect. So what is going to happen there here is your controllability matrix will not satisfy the rank. It will not be the full rank. and hence you don't have the power to control that one. The control is not directly affecting your system. So the system is uncontrollable. If you select L equal to not 0, 1 by L equal to 0, if you select 1 by L equal to 0, so there is no control. The voltage is not affecting your system, and hence the system will be uncontrolled. So you cannot do anything. So inherently, the plant can be uncontrollable, or the second thing is due to some disturbances or some noise or due to some other parameter, the system can become uncontrollable. In your particular case, due to the aging, suppose if the inductor is not working or due to whatever the reason, if 1 by L term has become 0 or L become infinity, then you don't have the control to effectively to control the complete plant. That is one thing what I want to say.
Thank you, sir. Thank you so much.
Hello, sir. Good morning.
Yeah, good morning. Good morning.
This is Parthiban.
Yeah,
Sir,
please tell, sir.
I have one doubt.
Yeah.
Sir, what may be the maximum extent that we can choose a pole? In our example, we have chosen 1,000, 2,000, 3,000, right, sir?
See,
So what
here
may
you
be,
have to, here you have two aspects you have to see. The first aspect is what is your desired specification, and
okay,
based
sir.
upon the desired specification, you have to ensure that the pole location needs to be selected accordingly.
Okay, sir.
If the settling time is very very small, then you have to select the very very large pole.
Okay, sir.
If the settling time is you don't want in the milliseconds to settle. If you want cell in seconds, you can select the pole accordingly. You can not select -1000. You can select as -10 or -20 or so on.
Okay, sir. So there is no limitations. If you want a very quick response, we can extend it to how much
Yeah.
extent it may be. There is no problem.
But you have to see the practical implication as well. Suppose in this particular case, I have given very unrealistic case of a DC motor where I want to settle the settling time is 0.006 or 6 milliseconds or so. But practically, due to the inertia in the motor, due to the various other components, whatever you do, you cannot able to get that specific. So that practical considerations also one has to see while designing the controller.
Okay. So only based upon some approximations or by trial and error method we are choosing the tools.
Not trial and error, based upon the practical consideration, you have to select the pole location accordingly.
Okay, sir.
Yeah.
Sir, did you send the video file? We are not able. I'm not able.
I am just sending the file because I'm responding to the questions, so I'm busy in that
Okay,
one. Now I will be sending that. Yeah.
Okay, sir.
Thank you, sir.
Yeah. Just give me a couple of minutes. Let me a pause from the questions as well. I just send you the PDF file. Now I am sending you the YouTube link as well. We will meet at 11:50.
Sir, when will the meeting start, sir? Hello?
Sir, no audible, sir. No audible.
Sir, you are not audible, sir.
Sir, you are not audible. అలా కాదమ్మా అడగడం. సిద్ధు తొందర పెట్టమ్మా. హలో సార్,
Yeah,
you are
hi,
not audible,
hi
sir.
everyone. Sir, I kept myself in mute. Just I'm giving the opportunity for others to do the. Yeah. Okay. So let's welcome back to this session. Okay. So what we will be discussing now here is, I hope all of you might have done that work. So now what I will be discussing is another problem. This you can take it as an assignment. This is little bit different from the one what we have already seen. We in the earlier classes, what we have seen that if ABCD matrices are given to you, then you are asked to find the corresponding pole placement controller. But here the problem is, design the pole placement controller for the below system to achieve the following desired specifications. Okay. So rise time should be less than 0.1 second, settling time, peak overshoot, and zero steady state error. So these are the four desired specification what I want. But here I have not given you the state space things. I have given you the transfer function. It is a seventh order transfer function, and five zeros and 7 poles. So now the first step in doing the pole placement design controller is you have to convert it back to the state space. Manual, I know that people are very good in doing the things manually, but this is a very difficult one because it has 7 poles, and you can write controllable canonical form very easily, but I don't want to do it manually. I want you to do it through MATLAB. So the hint here is you can convert this transfer function to state space by using the command tf2ss. So you go through this tf2ss command, what is happening in tf2ss command, and try to find out the equivalent state space model. And once the state space model in terms of A, B, C, and D is given to you based upon the code what I have shared, you can easily design the pole placement controller. So that's it from my side today. So this is what you have to do, and I hope you might have done this thing. So tomorrow what we will be doing here is, tomorrow we will discuss more on till now we had done two different independent controllers, PID controller and LQR. We had not done any contrast or comparison of these controls. So tomorrow what we will do is we will take maybe possibly a boost converter or the buck boost converter, a simple transfer function model. We will not go for the very complex, where different modes, continuous conduction mode or discontinuous conduction mode and so on. We will take a very simple buck or boost or buck boost. I will see what to take based upon. Today I will take the call on that one. And based upon that, we will be designing PID controller and the pole placement controller for that particular problem in the tomorrow's class. So I will take a quick questions if you have anything to ask me, a couple of questions, and then I will give you the quiz link.
Sir, Bharat, sir, this is Appara from Venkateshwara College, sir.
Yeah.
Hello?
Yeah, please
sir,
tell, sir.
coming to the DC motor, we will write the transfer function. Accordingly, we will write the program, everything. We will get some poles. Okay.
Yeah.
Sir.
Yeah.
So without that controller, we will get, let us say, rise time is something. With controller, rise time is, or settling time is something. Then what are the physical modifications? How we know the physical modifications? What we have to do it for the motor? Means in the supply side or motor side or winding side or whatever it may be. Suppose speed is
It
1500
is,
RPM, we did in 1
yeah.
minute. Now we have designed for half minute. Okay. So based on our polls, sir.
Yeah. So it doesn't actually need any hardware modifications if you're using the digital controllers. So what the actually implication here is, if you mean to say that if the speed of the DC motor, if you want to achieve in a very less time, then what is happening here in the control side is you are giving the voltage control very fast. So it is the voltage controller which will act. So basically it is a voltage controller itself. So if you see that if you want the speed to be in less than 1 second, then your voltage should be your voltage controller should act in such a faster way that for the power electronic voltage controller, so that it could able to give the response very fast. So how do you control the voltage controller? It is by using the gate circuit controller, gate pulses. If you control the gate pulses accordingly, so which will then control the power electronic voltage controller, which hence will accordingly give the corresponding voltage to the plant. Basically PWM control techniques or so on. So like that it happens.
Okay, sir. Okay, sir.
Yeah. I have already activated the quiz link. I have sent in the group before a couple of minutes. If anyone wants, they can do it. Yeah, if anyone is having any couple of quick questions, then I can answer. Otherwise, I will wind up the today's session.
Sir, we are expecting some more inputs from you, sir. Sir.
What inputs you tell, sir? What inputs you require, you tell me.
Sir.
Because you are a faculty and a professor, and
Sir.
you are expecting I have to see the students' point of view also, sir.
Yes,
This is
sir.
not
Yes, sir.
FDP, this is SDP. So because
Yes,
the
sir.
people have not yet completed this work, what I have given.
Okay,
Yeah, you
sir.
can tell, sir. You can tell your opinion. What
Yes,
more you want?
sir, till now I have gone through machines, power systems only, sir, specializations. So I am the somewhat like a beginner to the control systems, sir. So these things are somewhat new to me only, sir.
Okay.
Thank you, sir. Thank you.
No, you tell what additional things, what more things you
I
require. I
mean,
will
some
tell you,
more
sir.
example problems. Just you have given one exam solved problem, simulation program, and Simulink everything. So likewise.
Yeah. I have given another problem for you to do, right? The assignment problem. You can see every day I am giving one assignment problem.
Yes, sir. Yes, sir.
One I'm solving from my side. I'm giving you the code. I'm recording the video and sending you. And I am asking
Okay,
you
sir.
to do one. If you have done this class, the paper,
Fine.
whatever,
Yes, sir.
is,
Fine, sir. Fine, sir.
Yeah.
Thank you, sir.
Sir, excuse me, sir.
Yeah. Yes,
sir,
yes.
Can you elaborate the paper yesterday what you have given as assignment, that non-linear DC series motor modeling, sir? I have gone through the paper, but I don't understand clearly, sir. Can you elaborate for a few minutes, sir, so that we can try our answer room, sir?
Okay, so let me explain you. I don't have the paper now, but I will explain you what is in that paper. So this is actually the nonlinear plant. The nonlinear plant is given in that paper, and the first thing what you have to do is, it is not the linear ABCD matrices are not given in that paper. The first thing is, from the nonlinear plant you have to find the ABCD matrices. How to find that one is the Jacobian approach. So you have to take the partial derivatives of this nonlinear equation with respect to the state to get the A matrix, with respect to the U to get the B matrix. Once A and B matrices are obtained, then the process whatever we have done is exactly the same thing. So I have asked you to derive the I have asked you to derive the PID controller for that one, but not the feedback linearization method whatever has been given in that paper. So my idea is, take the plant, nonlinear plant from that particular paper, do the linearization by using the Jacobian approach, and then you apply the PID controller. It is not about the feedback linearization or whatever given in the papers. Yeah, please.
Hello, sir.
Hello. Yeah. Hello.
Sir. In yesterday's class, we lost some due to some network issue. I couldn't hear the half part of the class. So, can I get the recorded video of yesterday's session so that I can go through?
I already sent that 15 minutes or half an hour two different videos in which you can able to get how to design the PID controls for both the things. Actually, I'm also trying to get this, because generally this recorded video I'm recording in the online way. So generally they send the links to me. Due to some issues there, the links are not getting from the past 10 days because my trial version is over, or I don't know. I'm not saving on my
Okay.
computer due to the lack of space and other things. But the thing what I sent, the YouTube links, in that one complete explanation is given, and you can follow that one to design the PID controllers,
Okay,
auto
sir.
tuning,
Okay, sir.
everything has been discussed in those two links. Yeah.
Okay, sir. Okay, sir. Thank you.
Yeah.
Hello, sir.
Yeah. Hello.
As you said, just for linearizing a nonlinear system, we are using Jacobian, and one more thing is
Yeah.
Taylor series, right, sir?
Yeah. Taylor series approximation. Yeah.
Sir,
So the Taylor series approximation is nothing but if you express the nonlinear equations in the Taylor series approximation, you have to
okay,
consider only the first order terms, and the first order term is nothing but the Jacobian, and you have to assume that the higher order terms like Hessian and other things as zero. So the first order term is nothing but in the Taylor series is the Jacobian, or the partial derivative of the plant with respect to the control input will give you A matrix, with respect to the states will give you A matrix. Partial derivative of the plant with respect to the control input will give you the B matrix. Uh,
okay.
if you substitute the corresponding operating points, you'll get the A and B matrices accordingly.
But we don't know how to do that, sir. If you have any materials, then please upload in the WhatsApp
Yeah,
section. It
I
will
will
be
tell you
useful.
one small hint. You can use the MATLAB command Jacobian, Jacobian. In the MATLAB help
Okay,
space Jacobian, if you click that one, everything will come there.
okay, sir. Then one more doubt, sir.
Yeah,
This was the question I already asked in the morning session, and that is how to
yeah, yeah.
find a particular pole for getting a system, that is for getting a faster response. But
So
for simulation itself, there is no problem. But if you are going to implement practically, we need to consider the practical constraints in the system, and based on that, we have to select the
yes,
poles.
yes,
Just like you
yes,
said, do
yeah.
you have any supportive materials for that, sir? Because
Pole.
if we are
No,
searching,
see, every plant will have its own desired pole locations. You have to select. If you say the
okay,
DC
sir,
motor, what I have today, I have told if I want very faster response, which I want,
okay, sir,
6 milliseconds or something like that. So that's why I have placed the pole at very far away. In some cases,
okay,
what is going to happen here is, if you place, sometimes the pole's locations can also get saturate the response. That means if you place
okay,
pole at -100 or -1000 as well, you'll get the similar response, because
okay,
after the certain pole location, from the imaginary axis, there is the you cannot see much improvement in the response as well. So that can also be possible. So that's what I'm saying. So different
mm,
systems have even for the same system, if I want different desired specifications, I have to choose
okay,
the desired pole location accordingly. If I want 1 second, then I don't want to place my pole at very far away. Suppose if I
right,
want 0.5 to 1 second, if I want the settling time in between, which I have not constrained, so that is called the constrained settling time. I want 0.5 to 1 second. Then accordingly, I have to choose the poles in a very intelligent way. So I cannot place very far. If I'm placing very far away, then the settling time will be in milliseconds. So there you have to choose. So that's what I'm saying. So based upon your application at hand, you have to, as a engineer, control engineer, you have to specify your own desired specification. If it is like
yes,
fighter
sir,
aircraft, where we need
okay,
very fast, so it should be settling time should be in
okay.
few seconds. If it is a
The
nuclear reactor,
manual,
which is very slow, you need in hours.
yes.
So that's what I'm saying. So every
And
desired
aircraft,
specification.
if you go for aircraft, we need maneuverability. That is a major problem in
Yeah,
aircraft.
of
That's what.
course, of course, of course. Yeah, yeah.
That's what. Since we are beginners, instead of going to the net and searching all, if we are having a direct material, then we can grasp it
See,
easily. That's
sir,
what I'm
if
saying.
everything I cannot give the spoon feed, sir, please put some effort from your side as well.
Okay,
I'm
sir,
giving
I
all the
understand.
inputs. I am giving all the inputs, but still, if you want me to feed to the silver spoon, it is, please put some effort, sir. Everything is
Yes,
that
yes,
application.
yes.
That's what I'm telling. For different plants,
Okay,
different thing is there. If you try searching with that one, at least you can do that one, sir. Because that for that
yeah,
you don't need any special efforts.
I
Yeah,
understand, sir.
yeah.
But
So
is there
don't
any
think in that way.
trouble?
But I want you people also to put some effort. I'm
Sure,
daily
sir. Sure.
putting a lot of effort in recording and trying my level best to give you. So I expect something from you people as well. Some commitment,
Thank you.
nothing more than that. I don't need anything. So just the
Okay,
commitment
sir.
is required. Yeah.
But is there any thumb rule, sir, for selecting such polls for a definite system
Yeah,
like that?
there are some rules. I will say the book by Friedland. You can select, you can see the book by Friedland. Generally, it depends upon the natural frequency, what you want, and the damping of the system, what you want. Based upon that, you
Okay.
can select the pole placement as well. So suppose if you want your system to have the natural frequency closed loop to, let us say, 10 hertz or 10 radian per second, and the damping as under damped between 0 and 1. So there are some thumb rules for that one. So you can see the book by Friedland, Control Systems by
Friedland.
Friedland. Yeah,
Okay,
Friedland.
sir. I will refer it, sir.
So that
Thank you, sir.
reference I will give you. I will give you the textbook reference in the WhatsApp group. You can see that one. Yeah.
Thank you. Thank you so much, sir.
Yeah. Yes. So I'm winding up the session. Already the quiz has started, and some of you have answered this quiz. Please put some effort in, in what I can say, that in answering the quiz, because simply if you keep ABCD, you will not get the full score. Yesterday, none of you could able. The first quiz was very easy, where at least 10 of you could get 10 out of 10. Yesterday, none of you have got, even I think 9 as well. All of them are less than 9. So try to put some effort in getting the maximum. Yeah, maximum marks. Okay then, guys. So see you tomorrow. Thank you.